Misdiagnoses affect around 12 million adults in the US every year. This is a considerable problem, especially since America is supposed to have some of the best healthcare technology in the world. One way to try and solve this issue of misdiagnosis is to take a closer look at how doctors actually diagnose patients, especially in those fields requiring medical imagery such as mammograms. Today's medical images are inspected by just a small number of doctors and radiologists. Despite their expertise, they are still just human and remain susceptible to overlooking potential areas of concern. This can lead to misdiagnoses, delayed, or even improper treatment, resulting in more complications and unnecessary interventions for the patients. Researchers have been trying to develop machine learning-based image segmentation methods to help combat this problem. These methods help highlight abnormalities in a medical image, such as a mammogram, which could be potential tumors or cysts. It's like using special glasses that zero in on the regions of interest while blacking out all of the other irrelevant background noise, enabling doctors to pay special attention to them and therefore arrive at a better diagnosis. The major barrier to classical machine learning in the medical space is the lack of suitable data. Creating a large enough dataset requires a lot of time spent by experts manually labeling images for the model to be trained on, which comes with prohibitively high costs. Without a large enough dataset for training, a classical machine learning model will suffer from poor performance. This is where we tried to improve with our work in this project. We experimented with applying a hybrid classical quantum machine learning pipeline to improve image segmentation in mammography to see if we could perform better than the existing state-of-the-art classical machine learning models. We employed a well-recognized dataset in the field called InBreast, which is a collection of a few hundred labeled mammography images. Unfortunately, a few hundred is far from enough, as a deep learning neural network will require thousands, if not millions, of images to perform well. To help with this, we used data augmentation techniques, such as artificially increasing the diversity of the training dataset by rotating and adjusting the contrast of images, which helped us increase the data usable for training. We also employed a quantum image processing technique known as quantum filters to enhance the classical UNet model. Quantum computers are able to exploit the laws of nature to enable computational methods which are better suited for complex data analysis, which would otherwise be prohibitively difficult for classical computers of today. These quantum filters can enrich features in the dataset, which can in turn help enhance the efficiency of the training process, decreasing the total number of images required to train an accurate model. We then integrated our quantum filters into an existing classical imaging segmentation model called connected units, thereby forming our hybrid classical quantum machine learning pipeline. We are still working on getting the final results from this pipeline as we speak. Looking ahead to the future, though, the core concept of our work, namely quantum-enhanced image processing, could be expanded to benefit other areas of development outside of medical imaging, such as astronomical research or autonomous vehicles. Thank you.